Here in this problem, problem number 10 for our applied algebra problems, we have an equation for I, the moment of inertia, but we're trying to solve for D, which is the height of the cross section. This is very common if we know we need a particular moment of inertia to resist a certain load in a structural system of a building. Then we're down to choosing which type of structural member we're going to use depending on the height of the cross section. So we would want to solve for D in this case so that we can get the smallest possible cross section, which will be the cheapest, to achieve our moment of inertia that we need. You can see from our equation that the height impacts the moment of inertia the most because it's being cubed. So if we wanted to increase the moment of inertia without drastically changing the size, here's where we would do it with D. So that's what we're doing. So we'll solve for D. So we'll start with the original equation and then manipulate the equation. Let's multiply by 12 first to get rid of 12. I'll rewrite and we'll divide by B on both sides. And then we'll finally finish it off by taking both sides to the third power, or the cube root, which will be the same thing, to get D equals cube root 12I over B. We can plug in numbers here, which we have I equals 6.5 inches to the fourth and B equals 7 1/4. 12 and then 6.5 inches to the fourth over 7 1/4. There we go. Let's solve this thing. Let's plug in the numbers with our calculator. So 6.5 times 12 equals 78, divided by 7 1/4, which is 7.25. And then we will take the cube root, which I don't have a button for that on my calculator. So what I'll do is I'll do an exponent and then a parenthesis, 1 divided by 3. It's the same thing as 1/3. There we go. And then press equals to get my answer of 2.20. And then it keeps going. And we are to round to the nearest eighth of an inch. So it's either going to be 2 1/8, which is 2.125, or 2 1/4, which is 2.25. And this is closer to 2.25, 2 1/4. So we'll round it to that, 2 1/4, which is just 2.25.